Hello and welcome to High Voltage Engineering. We are on the topic of generation of high voltages and current. This is module 2.7 where we are discussing generation of high alternating voltages. Now in this high alternating voltages, one topic is generation of high frequency AC voltages. We have talked previously about the generation of high voltages in our normal frequency. Now we are talking about the high frequency. Now before that we need to understand that why do we require the generation of high frequency. So it is required for the rectified DC power supplies. So the rectifiers for the DC power supply, the higher the frequency, the more smoother will be the DC power. So that is the reason higher frequency AC voltages are required. The second use is the testing of electrical apparatus for switching surges. High frequency, high voltage damped oscillations are needed, which need high voltage, high frequency transformers. So it is also for the testing purposes of switching surges. Okay, and high frequency, high voltage damped oscillations. So in order for testing the apparatus for switching surges or high frequency voltages, since the switching surges that are surges, a sudden increase in voltages or current due to any kind of switching in the circuit breaker or any other faults. Okay, so these kind of surges transmit in the entire power system. So these surges has no particular frequency and most probably they have a very high frequency. So in order to test the apparatus for surge protection, these high frequency AC voltages are required. Now we'll talk about the advantages. So the first advantage is the absence of iron core in the transformers and hence saving in cost size. So when we using our transformers for the high frequency, there is no iron core, so there is a lower cost is there. The next is that pure sine wave output will be present. The third advantage is that slow build up voltage over few cycles and hence no damage due to switching surges. Okay, so during this frequency there is a slow build up of the voltage for a few cycles, and that is a reason there is no damage due to switching. Okay, and the third advantage is that uniform distribution of voltage across the winding coils due to subdivision of the coil stack into number of units. So when we are using for the high frequency, the windings are in groups. Okay, so that creates a uniform voltage distribution along the winding. So one of the instrument for creating a high frequency high voltage is the Tesla coil. Okay, it is nothing but a high frequency resonant transformer. Okay, and now it is nothing but a doubly tuned resonance circuit. Remember what is a resonant transformer or a resonance system where the inductance and the capacitance cancel each other out at a particular frequency. Okay, so we'll go for the general description of the Tesla coil. The circuit diagram of the Tesla coil or the equivalent circuit diagram is given. You can see there is a supply, there is a spark gap which is connected to in parallel with a capacitor C1 and an inductor L1. An inductor L2 is in mutual inductance with L1 and is again connected in parallel to another capacitor C2 across which the voltage is obtained. The high frequency voltage is obtained. Okay, so the primary voltage rating is 10 kV and the secondary may be rated to as a high of 500 to 1000 kV. So basically you can see the transformation. So in the primary side it will be of 10 kV, and on the second side it will be 500 to 1000 kV. Okay, the primary is fed from a DC or an AC supply through a capacitor C1. A spark gap G, that is shown there, is connected across the primary, is triggered at the desired voltage V1, which induces a high self-excitation in the secondary. The primary and the secondary windings, that L1 and L2, are wound on an insulated former with no core, that is it is air core. Okay, so this high frequency transformer is of we do not have any iron core, but it is of air, and it is immersed in oil. The windings are tuned to a frequency of 10 to 1000 kilohertz by means of capacitors C1 to C and C2. Okay, so this is a basic description of the Tesla coil. Now we'll talk about the coils. The primary coil is wound on an insulator fiber tube of about 1 meter length to represent a cylindrical helical winding and consists of a few of tens of turns, usually copper string and or tubing. So basically the primary coil is nothing but it is a is wound on an insulator fiber. It's basically, if you have seen Tesla coils before, it is a coil that makes a bigger coil. Okay, so you can go in the net and check the shape of the Tesla coil. You will get to know. The secondary winding is spaced quite away from the primary winding on another concentric fiber or Pyrex tube, which with a few thousand turns. The whole assembly will be immersed in a tank of oil under pressure, with separated bushing taken out of the primary and secondary winding. The primary winding is supplied through a high voltage capacitor rectifier unit rated at 10 kilovolt and 10 to 15 kilovolt or more, and the power rating of the transformer may be 10 kVA or more. Okay, so this is description of the Tesla coil. Now we'll come to the description of the output. The output voltage V2 is a function of the parameter L1, L2, C1, C2 and mutual inductance M. Usually the winding resistance will be small and contribute only for the damping of the oscillations. The analysis of the output waveform can be done in a simple manner, neglecting winding resistance. So since it is we are talking for a resonant transformer, it is nothing but a resonant transformer. So the voltage, that is output voltage, will be a function of this inductance and capacitance in the circuit. Okay, so we'll talk about the analysis in the next slide. So let us check the calculation. Okay, so the peak amplitude of the secondary voltage is given by this expression V2 max. Okay, where you have this expression E and A, that is in terms of a ratio of LC. Okay, so more simplified analysis of the Tesla coil may be presented by considering that the energy stored in the primary circuit in the capacitor C1 is transferred to C2 via magnetic coupling. So it is, you can see there is a transformer, the C1 is on the primary side, C2 on the secondary side. The energy that is stored in C1 is transferred to C2 via this mutual coupling. If W1 is the energy stored in C1 and W2 is the energy stored in C2, and if the efficiency of the and if the efficiency of the transformer is given by W is equal to half C2 V2 square. Okay, from which we can have V2 is a product of V1 into eta C1 by C2. If the coefficient coupling is large, the oscillation frequency is less, and for large values of the winding resistance and K, the waveform may become unidirectional impulse. So this is the case where is a particular case for the Tesla coil. So if the coefficient coupling K is large, okay, you have a large coefficient coupling and the oscillation frequency is less, and for the large values of winding resistance. So there are three things. So the coefficient coupling K is large, oscillation frequency is less, and the winding resistance is high. The K waveform may become a unidirectional impulse. So the calculation here is so you have to remember the formula. Okay, I will explain in another chapter, another slide, another class, the background calculation of the Tesla coil. So as of now, keep this values in mind. Okay, so just one sec. So yeah, we as I've told you about the calculation. So let us go for the consider the capacitor C be charged to a voltage V1 and the spark gap is triggered. So let C1 is charged, okay, and the spark gap is triggered. That means there is a shorting in the spark gap. Okay, so what happens is that the current I1 flows through the primary winding L1 and produces the current I2 through L2 and C2. Okay, so we have two equations. Okay, so on the left hand side you get two equations for the two different circuits. One for the primary circuit, we have a V1, that is a supply, and a voltage drop across the capacitor. Those who remember the circuit analysis, so it will be easier for you to understand. Okay, plus the L di dt, that is the voltage drop across the inductor, and for the M it is the mutual inductance. Okay, and for the secondary side, since there is no source, we have a 0 on the left hand side and equal to again the voltage drop across the inductor and the capacitor and the mutual inductance. So if you go to the Laplace transform, so you get the equation on the right hand side. Okay, so if you do the solutions of V2, you will get the V2 in terms of this expression. Okay, so you can do the calculation by yourself. So these are the calculation data that I have given. Okay, so this is the end of the lecture. Thank you.